at the back end of Mo's talk, I like I guess I call them those sort of enigmatic structures that he was appearing to map where the placer was, and we actually had an assignment, although it wasn't explicitly told to us, in the 40-mile area last year. It was sort of tasked with a similar thing, and it was a very, very interesting but frustrating but informative exercise in that comparing in that environment as occurs in a number of places both in the Yukon and Alaska. It hasn't been glaciated, and so you have a regolith development that can actually exceed the depth of investigation of the Digim system. So you're seeing the regolith, and what does that tell you about the real world? Well, it's still part of the real world, but it's kind of like a ghost in some respects. The extreme physical properties are changed so that the intrusive rocks and the limestones, which would be very high resistivity, if they've weathered down, they'll start to take up a lower resistivity, and alteration will sort of, I'll say turn into mush in some respects. But structures often get preserved. You can still see linears through the data, depending on how much tectonic activity is present. But what was really interesting in this area, they had I think a reasonable junior came in and did some work. And in year one, they produced a geology map around these showings. They did some geochemistry, they obviously did some mapping. And they came back in the second year and produced another geology map. This is all like years before we arrived. And the next geology map didn't look anything like the first one. And neither of the geology maps looked anything like the geophysics. It was a very interesting, where are we going sort of story. And I felt for the geologists because they were probably typical Cordilleran or from the middle of Canada or something, and unless they've been to West Africa or Brazil and seen regolith, they don't have a clue. And it's in your backyard, and it's affecting the surveys and your ability to map. It's affecting the geochemistry. So there's this overprint that going into an area and just sort of, with geophysics, we have some advantages, like with the magnetic survey in particular. It's not affected by these conductivity effects or whatever. It's going to see what it's going to see. But electromagnetic techniques, that's in your face. You're going to see those effects, even if you're not aware of them. It's Abraham talked about merging data sets and the rest of it, but you almost have to. One of the products that maybe in 10 years' time, or as a retirement project for him, is sort of put a map together and show what the estimation of the cover is over where these surveys are. Because that would help enormously in not only challenges you'd have in mapping, but how to interpret geochemistry, how to design programs when you've got 60 or 100 meters of weathered material versus more like, Mo's case. He had wonderful outcrop, I would call it, that he was hitting with his giant hammer. So anyways, those structures that he was teasing out towards the end, I thought, well, they may exist in this area I was working, but it would be very, very difficult in that setting with that amount of cover. It certainly probably never mapped them. We came up with 5 small intrusives that weren't from the geophysics based on the resistivity, that it was no indication of mapping whatsoever, and they were really close to some interesting mineralizations. Like, okay, maybe this is what's happening. So this is a tour. It's kind of like Abraham took us on the 30,000-foot voyage, and this will get down at maybe 20 or 15,000 feet over some of these, say, called intrusive-related systems. And so, this is a model that Jeremy Richard, well, he's been working on it a large part of his life. Academic, specializes in porphyries, and I find it interesting because we finally got a geologist to put geophysical characteristics, chargeability, resistivity, magnetic sus, alteration, mineralization, and geology for these things, and then depth of erosion and type responses. And we all kind of knew this in a way rolling around in our heads, but it really helped when somebody as cluey as Jeremy actually put it down on paper and sort of say, figure out where you are and what to begin to try and, like that casino example that Adam had, probably in that case, the difficulty in seeing what we often see, these pyrite halos are between the philic and the propylitic zone. They didn't get far enough out. Plus, the other thing was that IP survey probably had a 200-foot dipole, and they probably went to N1 through 4, and so they would have never gotten through the oxide zone. They didn't know that, or at least if they did know it, they didn't act like they knew it when they had the geophysicists do the survey, and they might have had a system that simply couldn't have seen deeper anyway. So, a great swath of ground with a huge amount of potential, obviously in gold, porphyry systems. There is some I didn't bring any of it in, but there are a series of publications, and some good joint ones, straddling the border, looking at particularly the magnetics data. So if you haven't seen those regional ones, Sanchez was principal author on one that came out in 2014. I think there was another one in 2012 that relied heavily on the regional magnetics data. Very, very interesting stories, but just really the beginning, 500,000 scale type assessments. So that's not really part of what we got stuck in here, but it's where that data, like from the USGS and from the DGGS, ends up. So the model, lots of the deposits are associated in some ways with an intrusive system. This is, I think Hart stole this in part from Francois Robert's effort some years before that. But there's certainly a lot of the things, we talked about the BIF systems or the disseminated ones, and certainly the ones directly associated with intrusions are fairly significant, and we'll be looking at a couple of those through the eyes of the DGGS data. And then how do you find more? What do we see as far as a characterization, and how do you find more of them? So this was sort of a list that I came up with, and partly with this work we were doing last year, is sort of say what's some intrusive related ones, some porphyry related deposits. Tetlin, I guess when they talk, it sounds like a skarn. I'm not sure if they know really, but it sounds like a skarn. And then there's some other polymetallic ones floating around. I think chicken is actually near where fish is. Carbonate replacement style. I mean, that's a well-developed and understood model in Mexico, and there's some in southern Arizona, but I'm not sure if it's really been recognized officially. What did somebody say? It was a. It wasn't a. The Greens Creek was a Greens Creek model. It was sort of like it was different than Kuroko, and if it's different, it may be a cousin as opposed to a sibling sort of thing. It's related, but not directly. Here's an image from the Sanchez paper. He did some characterization of large-scale intrusive bodies and things like that. Next image here, we'll snapshot into the 40-mile, 60-mile area and further to the west. And this is a data set that also is available through the SGS, which is the Bouguer gravity. And you're not going to be finding, it's nowhere near the resolution that Adam spoke of you get with airborne surveys, but it's telling you fundamental things about the crust. Has to be. And with that, why are these intrusive systems where they are? It's all related. It's the same, they're living in the same zoo as the mag and everything else. It's just sort of like, we may not have explanations for these patterns, but they are true. I mean, there's enough data in that map to know that's reasonably reliable. And that's mineral occurrences from the database. And look at how they wrap around the edge. That's not coincidence. There's a frickin' control, some major structure. Grouping on the other side, grouping on the edge there. Go figure. Anyways, is that good for them? They're on the other side. It looks like they're on the other side of the Bering Sea or something. There's that big porphyry Taurus up there. So I can't pretend I know what's going on with this data. There are people that do get the chance to spend some time and stare at it. But when you see trends like that going through, you say, wow, okay. And this information is coming, you see some of the images from Olympic Dam, the Gawler Craton. They got images going down 50 kilometers with their seismic, with their potential fields. And they know they're seeing stuff down at those depths that's is associated with the plumbing that's producing the Olympic Dam deposit. So there's no reason why it shouldn't be working up here as well. Even though it's a very complex accreted terrain package, there's still fundamental things going on that we can map. So that's the outer space view. Here's jumping down into the messy part of the world. When you actually look at, and that's a geology map actually. There may be a better one, but I think that's the 2000 one that came out of the Roundup. And that looks like some sort of Amish quilt design to me. I'm not quite sure who dreamed that up in terms of, where did all those frickin' straight lines come from, man? I mean, ladies. It just, anyways. You got the deposits here, which is great. I'm glad they had those. Here's a terrain image. Here's our RTP. And there's a conductivity map. And you know, it's a very humbling experience when you look at some of these things and you say, well, the mag feature actually seems to run up between these two pieces of the deposit, the larger one being on the southwest side of it, and then you have this big low. So what's important? Are you drawn to this as being sourced somehow? A little small, intrusive heat engine or something? Well, that's not really what the geology describes it as. They do come up with a bit of a description, but when you look at the geology map, and you put yourself over here, that mag feature really doesn't get well identified, because if you want to say it's coming from the red unit, okay, I can't quite read but you see there's a piece up here, and then there's a fault offset down here, another piece up here, and you go back and look at the mag and say, well, there's a little bit of it, but that piece on the north, it sits there okay, but what about, going back down here and further up, and there's another one over there. That one sort of shows up, but the one up in the far corner doesn't really show up quite the same way. So the mag I would give it 4 out of 10. The EM, I look at it in terms of helping you with sort of understanding. EM is like, oh, gosh, I don't know what to make of that. I mean, that could be a drill rig or something. At the time, I mean, a singular anomaly like that, it's not really geological in the normal sense of things. And we do, with our modern systems, we can actually find drill rigs. That's been documented. We've documented it a number of times. But, is this big sea of resistive rock, is that the important thing? Because if you come in and you want to find a target, and you want it to be there, you can do some pretty weird things with the data. But it could be that you're tricking yourself by the scale that you're working at, and you're not really being fair.
Can we go back? I just have a quick question. How confident are you on the mapping of the deposit itself? Is that based on a lot of drill data, or is
I would say that's where the rubber hits the road. The geology is probably much less certain, but I would say those outlines, and even back in 2000, they would have had a pretty good idea. There could be more, but where they have the lines I would say, was reliable. We don't know what they've missed, because we don't really know the intensity of work and other. So there may be a satellite zone. See, there's a little smidge here and here. So it's suggestive, and I think those are probably scout drill holes. They just haven't shown all the holes in the area in there. So, yeah. Maybe someone here knows a lot more about Oga than I do, but. And I've looked around for a more recent map, and I guess Sumitomo doesn't feel obligated to publish that sort of thing. So. Go team, right? They're okay, nice. I just had some figures, so 9 million tons and really nice grade. So definitely something you'd like to find more of, if you could. Here's a step back, okay? So now I've tried to bring us all down to earth with the zoom in, and here's the deposit location. Again, there's that little mag high, and here, now we see this big tongue of low magnetic response, wraps around through here, and it gives us a feeling it's got some overall coherency, extends down to the south, and then there's some little high in layers here, and then kind of a deep, kind of quasi-bathylitic source here, and definitely something fairly large and deeper through there. This is the apparent resistivity. In this case, the high resistivity are the warm colors. We're going up with numbers because it's calibrated in ohm meters. And there's that tongue of mag low. I've just outlined it because it really isn't too obvious otherwise. And you say, well, how is that package different from that one? Kind of a hard story to say to me. And then when it comes down through here. So, and there's a couple of surveys I think went into this, and we leveled it at one point, but we didn't, we'd have to go back and maybe look at that vintage thing, Adam, and just see if I don't see any TARs, I don't see any real step things that would be suggested that we've pooched up in this. We do a pretty good job of leveling even if we don't know why we're leveling it.
We have theirs, they level too. That's published now.
Yeah. So that was, the gravity setting for Pogo was pretty interesting. The mag looks also interesting. And this gets to one of the things that Abraham mentioned. We may need to go to resolutions greater than what most of these surveys are done at, which was 400 meters. A modern survey for these sorts of deposits, probably nobody would go wider than 100 meter line spacing. 4 times the resolution of these surveys. And I think that's one of the things, we're on the cusp in a lot of cases. We're seeing some of the story, but we're not seeing enough. Even Mo with his did 200 meters, right? I mean, he's not even a minerals guy. I mean, he's a geologist who's spending government money to make a better map. So he didn't worry about targets in the sense that that wasn't the job of his particular survey. So I'm thinking that because we've looked at a number of these over deposits, they're sort of like, if we just had slightly better data, we might see some structures that would be compelling from the point of view of why a particular deposit somewhere. There's more you can do with the data for sure, but you know, it is this is the old term, it is what it is. It's good for maybe getting in there, but it's a challenge. So there's the RTP again, up on the left, and there's Pogo sitting out on the like a diving board. That's the gravity, but the data here is pretty sparse right around Pogo. So you know, you say, well, okay, grain of salt. If you had roads, you could add more. The guys in West Australia now are flying airborne gravity to basically supplement their large amounts of mag and radiometrics over the years. Some jurisdictions are pushing out to get gravity. Not too many governments, although they did a big survey in British Columbia a few years ago in the Quesnel Trough. But that to calibrate, and I don't know if you in the room know this, but what has happened in Alaska is unique within this country. There's no other state that has the database that's available here. Minnesota's got some good mag because of the iron ore stuff. But even Nevada, I mean, they're pikers, you know. All the tax revenues is just, I don't know, build more casinos for somebody or something. But it just doesn't go into geoscience, that's for sure. So when it's come to do these sorts of analysis, we're very, very fortunate to have these data sets going back over 20 years. And you guys pay for it with your taxpayers' dollars. It's at least, it's good. That's the rest on so Fort Knox, this was another important one to think about from the point of view of, is there a direct signature? And without, it's the legal term, no harm, no foul, you're not really, it was found, and that's the important thing, but when you go back and say, look at this data, is there something that will tell you that would allow you to find the next one? So we see, and of course, well, I'll show you, there's this major, it's broken up, but there's certainly a line of magnetic features running through here, and there's another weaker one with wispy bits. And this sort of sits in a funny little gradient that doesn't really, it's not close enough to that high to really be considered like a skarn or a direct tie-in with it. The resistivity, again, we have, play with your minds. This one is ohm meters, but it's now The high values are in blue. I apologize. So very resistive around here. But that sort of piece looks geologic in terms of the size, but you know, the deposit itself is a relatively small feature inside. This much larger, there's 4 10 kilometers roughly by 6 kilometer block. What are these other ones? Are these on echelon? Or is that just me not having any sugar? You know, say, well, maybe it is. Maybe we're seeing something in the pattern, in the crust. It says, you know, one of these deposits occurs here and there might be some periodicity. I don't know. It's an idea. It starts with ideas. There's the geology that I can find. I think it's that GIS one you mentioned, Abraham. But so you look at the, I just did a quick and dirty etch-a-sketch thing with the mag and put this line around, and that line of dots sort of falls at the edge of that magnetic domain, and there it is right there. So on that map it says that there's more magnetic rocks going that way and less magnetic rocks to the north, and then that's where it falls in the mapping. Don't see it. It's there, pretty sure it's there. The top one's the same thing. There's some discrete features. There's one right here, just south of the deposit. Nothing. No character whatsoever. Maybe it's a different phase of the same intrusive. Maybe it's just 2 points where they mapped and they've just drawn they had a lot of pencil crayon of that color and they just filled it all in. But likewise, that one there, there's no indication of magnetic data, there's any zoning, there's any rock type change whatsoever. And this is a fairly common occurrence. I put the contours on here. Here's that mag high. See this black kind of ratty stuff? These other highs are sitting down here. So there seems to be an edge. I believe this is just a sedimentary cover through here, but along there. But there's nothing north of that line is indicated there. And then there's certainly not this major structure that lies, I'll call it a structure, right through there to the south. There's this thing, but there's nothing up in through here where it's strongest. There's no response whatsoever. So, okay, bit of a zoom in so you can see the relationship between that mag high and there's this little low, which could be a dipolar low, we call it, because of the dip in this. But the deposit outline, which is about 1 kilometer, here's a click, it's a little over 1 kilometer, but it's elongate, is outside of that low. So I would say, well, I think the location is serendipity, that that's actually not tied in with that directly, although it may be tied in with this on a different scale. It's not part of it, it's not like a scarm. Sorry?
Well, I said the red is the top of the ridge.
Okay, so the weather's high, yeah. So it's real geologically. So there's something in the rock that gives it a stronger rheology, but it hasn't been identified as a different rock type because it's not on the map. The map at that scale, anyways, has not captured that. But you know, I don't think anybody didn't do their job right. It could be that there's a station every 3 miles. And it's just they don't have the data density. The geophysics has the density, but it doesn't have the geological context to really know how to, you know, to say with certainty that should be how to interpret that. There's the gravity. A few more stations here because they had a road to define that low. So is this at depth a large intrusive body? And this just has come up along the side. It's a model, it's an idea. There's certainly nothing in the geology to either support or refute it at the scale that we're looking at there. Because we're going way to that gravity feature goes way off to the north beyond here. I didn't look that much farther, but yeah. So interesting stuff at the kind of the district scale. Not so much direct correlation at the deposit scale. Good resource. It was really hard to get that paper. Do I give the reference? On Fort Knox, it's in that frickin' CIM. That 95 volume on the porphyries, right? There's 3 in the series, and that was the last one. Somebody said they're going to do another one. It's up to print. You can't get it on Amazon, you can't get it on eBay. And the nitwits in Montreal didn't make a PDF copy before they got rid of all the books. They don't have a frickin' copy at the CIM headquarters of their own frickin' most important porphyry book published in the last 20 years. And that's where the paper is that has this information. But they said, it was interesting, they said it's a porphyry system, it's zoned, and it's got a low level of sulfides that I bet you $1 to a donut, if you did an IP survey, you would see an ambulance around. But nobody ran IP. Geochemistry worked for magic. So don't spend any more money than you need to. Next one is live and good. More complex, definitely. Here I don't have any sort of, I don't think 43-101 stuff, but you can guess based on drill hole densities in these 2 locations where the action is. There's our RTP, and gosh darn, what's that strange? There's that intrusive, the ester pluton over here, with a lot of showings, but rock samples. Not so much mineralization. Mineralization is pretty well much focused in here. I think those are some of the major structures. Outlined that Cambrian mafic block there, and then the black outlines are basically the 2 black outlines here. So I'm not sure if there's a fault separation between these. I didn't see anything particularly. We got these twins sitting out in kind of a motley magnetic response. No coherency around that pluton, certainly in the magnetic data. I mean, it isn't even, Abraham pointed out a few that were sufficiently intensely low, we could call them remnant features. But this is just a blah to me. It's definitely low, but there's really no character, nothing other than that little bit down in the south that's really taking place there. That seems to be capturing something there with this unit, which is the same as over here. It seems that this Cambrian package has this mottled appearance. So if you take that, is it a structural control in these things? That could be it, that the rocks themselves, you know, that there's something underneath it that's giving rise to these deposits. And maybe you have to step back and look at a bigger picture. We'll do that, see what we see next. Well, this is the same scale, but the EM. So the 7200 hertz data. We seem to see a bit of a resistivity high, the blue here. But this one gives us what appears to be a bit of a resistivity low. So we kind of have this dichotomy between the 2 zones, although they are in different packages. That could be an important factor. If we had some IP data over these things, some calibrations, you know, some physical properties that the IP would help us with, we might understand why, you know, that sort of, call it inconsistency is occurring there, but it doesn't make it easy. Well, here's a bit of a step back. I think this shows the limits of the survey. So there's this really strong, there's one of them is here, one of them is here. This big wrap around of this magnetic high, and this is sort of in this, it's still elevated and has that motley texture, but it's not nearly as intense as the rocks around it. EM-wise, say we've got this fairly large conductive feature here, and this relative resistive zone associated with the other one in there. So it's like, that looks interesting. I mean, that to me, that sort of suggests some large scale feature. We saw some trends at Fort Knox that were also trending this kind of flat east-west or northeasterly direction, but it was in the mag in that case. So there's some grain. I mean, Fort Knox is about sitting down about here, right? So there's certainly something in the rocks up there that's telling us there's these northeasterly, southwesterly features. And the geology does pick up some of that. Definitely, but it doesn't, it seems to be lumpier. We've seen the casino one. This is a tilt. Adam introduced it to us. And I doing this work on a case study development, I passed it along to Mo Colprin to have a look, because they updated their geology, very proud, they updated their geology this year for the area. And I said, hey, you know, I'd really be interested if you went in and did some further inspection about, you know, you see this wedge here, as Adam pointed out, the Dip Creek Fault is pretty well expressed, but there's this badge of magnetic high kind of bounded by that structure there, and then there's a bit of magnetic high in here, but then you go up in that direction and it changes dramatically, even though we have the same Dawson Range batholith rocks being mapped. And in this case, the black dots are the observation points. It goes up, it's valid up to this point, and then that part I don't have the actual data, but that's, you know, for 500,000 scale mapping, that's 100,000 scale. That's, I think, pretty reasonable geological data. We see that edge up in here with the snowcap metavolcanics. Very hard to sort of see that metamorphic piece up in there, but maybe it's coming into the low. This outline here that appears to be associated with this gigaton porphyry system really doesn't capture much coherency on the geology map. And this was a case where 15 years ago they did a large amount of mapping right around where the pit is, but they really never got out much. It's only been when the GSC and Yukon survey came in did they do the regional work, and they never really put the story together as to what could be going on in here. But what you see when you look at the 3D model is you actually have a cylinder going to depth that then arcs into this big guy over here. It's kind of like this is the mothership, and this piece is an apophyse here, and then the porphyry itself is part of that secondary story. So you have a very large mafic system that's expressed over here. Part of it has come up independently, and then the porphyry intrusions have been associated with that part of it. Anyways, there's no such discussion in any of the geological papers. Absolutely zip, right? They never looked at this as a place to. There's not even a PhD study on this. Most porphyries in the States have got 10 PhDs stuck onto a deposit, masters. But this guy got orphaned for some reason. I'm not quite sure. They're trying to get it permitted now. Heard that story. The ground mag is pretty neat. One of the phases, the patent, as Adam said, in the center, but it doesn't have a lot of depth extent. It's a fairly strong anomaly, but it doesn't go to depth. It's the feature over to the west side that goes to depth. The modeling helps tell us that. The big potassium anomaly going off to the west, to the northwest, what's that about? That's real. I mean, if you don't see a response, that could be shielding. But if you see a response, and you can't just say it's topography, because there's topography everywhere here, it's a mountain range. So, I mean, this data is from 1994. And other than a little bit of write-up by the guy who took the data, because that was his job, nobody's ever looked at this stuff. It's amazing. And this is 10% of a sheet this big, and there's another sheet beside it covering all this prospective ground. So yeah, they got the radiometrics. They just didn't do much with it. Hey, there's stories here, lots of stories. Saw that one before. Taurus was interesting to me. In fact, I looked at this one before I bounced into Casino, because it was near where we were looking. And look at Pica Canyon. Gosh darn, there's a mag anomaly. Bang, right associated with it. This is beside mag feature. This is next to it. This is maybe push, harder to say. But if you get 3 out of 4, that's pretty cool. What's happening here? What's happening there? Anyways, it's and this is some of the, there looks like, there's probably, that's a remnant feature there probably. And these aren't bad things because they probably are singular intrusive events of a different time stamp, that's all. It's chronology you're seeing. And it's discrete. So in Mexico, with the CRD deposits, we often see reversely magnetized intrusive bodies associated with the mineralization. There's something happened at a particular time in some of these districts that the Earth's field was reversed. Part of the model. There's a 10,000 foot wide IP anomaly associated with that. And I asked the guy I was working with, some of you know him, Harry Noyes, and I said, Harry, why didn't they drill it? And he says, oh, well, the chemistry wasn't right. Chemistry wasn't right. Yeah, okay. And now the core is on the runway, according to God bless. Here's that geology map for that area. To me, pretty interesting because you don't really know what's happening with porphyry systems at depth until you get down there. I don't think there's enough reliable means to do alteration mapping and analysis just based on the upper parts of the porphyry system. And that's why all these companies are exploring in Arizona now, because they're looking at resolution. You know resolution? It's down 3,000, 3,500 feet. There's a giant, massive sulfide anomaly. Well, the sulfides are there, but it's an EM anomaly sitting over top of that. That's down like 400 or 500 meters. No surface expression whatsoever. And that's where the ore body's expression is coming from half a kilometer down. Sure, it has to have underground mining, but to come in and just do superficial work around a porphyry system when you know the system is 2 to 3 kilometers, there's things that could be going on in those that can surprise you big time. They are really big systems. There's the IP anomaly. All of this hatching, 1996 work, IP anomaly outlined. So there's our scale bar. Okay, I can do miles. 1, 2, 3, 4, 5, 6 miles. 6 miles wide. That's one of the biggest IP anomalies I've ever seen in my life. Period. That is a monstrous system. It's like a transformer, more than meets the eye. Okay, Donellan Creek. You had a much better image than I could find. You didn't zoom in on it, but remember I sent you that email? I couldn't find the surveys that covered it. So I went back to that old publication, so I apologize for that, because I should have compared
I
notes.
should publish the one I had. It's on my wish list.
You haven't published it?
Well, the individual surveys are, but I had, thanks to CGG, a merge of all the surveys. It's just not published right now.
Okay.
I built the infrastructure to publish it, and I'm free in there. I'm adding again, I think about 5 more to add.
Map. Okay, so anyways, lots of resources.
I said, push these merge grids out there.
Very complicated geology. So we hope, obviously, that geophysics is going to be really simple. All I have in this case is mag, but anyways, I mean, this enormous, I guess the airstrip conforms to the northwest-southeasterly direction for whatever reason. It's sympathetic to that structural direction. But we have this very prominent set of dikes coming in, and then this zone of confusedness. Looks like some complicated fold structures. So when you look at the mag, and I think all those features have been dropped onto this image, and you say, holy crap, holy. I mean, man, that is one weird image. I mean, you can see components of that northwesterly grain. You certainly can see some of that northeasterly grain. The area of the mineralization, if you take that as the white bit, is largely in this low. And I say I apologize, I didn't have a digital grid, so I only have the contours that were provided in the, I think it was a 43-101 resource report. I should usually put the reference down. But, so this is an aeromag survey that was flown, I think, by Placer. And then it's been handed down to the owners, and now I guess Barrick has this survey. I don't know that they've added to it. In fact, I think the 43-101 said they hadn't added to it. So, in a sense, although we don't have maybe the scale required that the DGGS data would provide, because I haven't looked at it yet, that this low, how unique is that? Are there others? But that looks like a fairly anomalous package that could be, you know, either lithology or lithology / alteration effect that's giving rise to that. But this proximity to this magnetic high to the northwest is interesting. The way it comes around, so it bounds. So something here, although there's only one structure indicated here, I'd suspect that there's something going along that whole contact. These could be, you know, obviously real as well, the ones that are geologically provided, but they may not be having the same degree of geophysical expression. There's a little bit, you see maybe something tracing off there. But I thought that was a pretty cool image. This is published by the owners, the joint venture partners for Tetlin, because they only release the only data available is publicly released data that they've released. But this is so we use the word skarn. I use the word skarn. I think I've heard other people say skarn. And this is a magnetic isosurface. So it's inverted from an airborne survey. And it's moderate susceptibility range in this particular case. These bodies are modeled EM features. This red is the 5% sulfide shell. So here we can see, call it the story all coming together, where we have this magnetic chimney. We have within the chimney the sulfide body, and then extensions through that, and then outboard of that magnetic anomaly of other conductors that are at this stage not defined as being part of the ore resource. So geophysically, gold mineralization in here, conductors but not gold scattered around with a direct correlation with mag. So is that enough to call it a skarn? And they actually gave us the attribution. So we did the work, but we don't have a release to show it independently, so I only can show what's, say, available on the website. And they haven't pulled it down, so that's fabulous. This is another image from that survey. This is a little harder. You never know quite what they want to show you, but this is a conductivity map with the colors, and then they put it onto maybe a topographic surface. And here's their main story in here, peak, discovery zones. So that magnetic feature we're looking at sits right underneath there. There's another one over here, and another one up there. These chimneys that seem to have control over the mineralization. So. And then they're going into a big river valley over here. So just totally washed out in terms of response. Very, very conductive, and nobody's seeing really too much below that. And they have this TORS area over here with a number of anomalies. They've done, to my knowledge, a limited amount of drilling here. And they have another discrete feature here. It's kind of noisy in part, and I think this is in part, I remember Kurt saying they had about 60 meters of regolith here. And that made it was right at the transition for the DigEm survey, but they flew a time domain survey, the system that Adam talked about, the Heli-10, and that pulled out the signal much better. But we can't show those results, but hey, trust us. Okay, it's our break.